nanobiology, and we work on many types of biological materials, including dental materials. How do we make these things stronger, more corrosion resistance? We also work on this is something missing. This should be a figure here of spine, but it's not. But anyway, we work on hip joints. How do we make it more bioactive? We also work on cardiovascular products. For example, stents. These are things that you insert in the blood vessel to expand the blood vessel in the heart. If you have a problem, then they use it to expand the blood vessel. Also, we work on artificial heart valve, 心瓣膜. It's very critical because if the material is not good, then blood will clot on the surface, and then you have a problem. So we have to make sure that things open and close very naturally. All right. So these are the things we work on. We also work on industrial components. Being in southern China, there are a lot of companies in Putonghua, in Shenzhen. All right, they work on these things. They work on golf clubs. We work with them to make sure the golf club go further, the ball go a lot further, harder. We work on wristwatch, prettier, more long-lasting, jewelry, necklaces, glasses, cutting tools, blades. How to cut cutting material, or some industrial components. We do that, all right? So we did drill bits, how do you drill things and make the surface stronger, longer lasting. So these are the things that we do. We also have companies. I have a couple companies, one in Chengdu, one in Shenzhen. Our company in Chengdu basically makes power supply and also vacuum equipment. Our company in Shenzhen works on processing, 加工. So we do, for example, companies in southern China, they don't have the money or the space to buy the equipment. So they send the samples, the materials to us, so we can process them. So this is a very big business for us. So my students are in charge of this company. They're doing pretty well, making money, so that's most important. So we're very happy because we do basic research, we do applications, and then we do commercial activity. So we do everything, all in one line. So that, to me, is the way how research should be done. We understand basic science, try to at least. We explain the basic science, and then we use the knowledge to do something, to help people to make the computer run faster, or to make something more long-lasting, and then we make money. Use the money, we go back, support the research, and keep going, and bigger and bigger and bigger. Why not? Are you following me? Any problem? Too fast, too slow? Beautiful. All right, we use a number of different techniques here. You remember that vacuum chamber? It's just a big vacuum chamber. Here, how we establish a plasma, we input some gas, usually a gas like oxygen or nitrogen or something. And then we apply some energy using RF, radio frequency typically. And that energy is coupled to the plasma. You create ions, electrons, and they will collide with each other. And if you have a magnetic field, they will go around. You know your physics, right? Straight line, magnetic field, it goes around. Right hand rule, right? They go around. And then they will collide and create more ions and electrons. If in equilibrium, you have a state of plasma, which is very energetic, having a lot of ions, electrons, and everything. Now here, if you have a sample stage inside, you put in a sample material you want to treat, you apply a negative voltage. Now what's going to happen here, this is negatively charged, right? All the positive ions will get attracted toward the sample because of the polarity difference. Now, these positive ions, or oxygen ions, or hydrogen ions, or whatever, they will be attracted, and depending on the energy, either implanted or deposited on the surface of the sample. So you can do deposition, you can form a film, a coating, or if you increase the energy, they will be penetrating into, with some depth, and that's what we call implantation. Ions are being implanted at some depth toward the sample. And this is a very, very useful technique, all right? And if you look at this, how we work things out, since the whole sample is under negative bias, so all the ions will be attracted simultaneously. Now supposedly I want to implant into, let's say, this bottom, all the side, okay? The normal way is to use an ion beam. So we can implant here. To implant the other surface, you have to rotate the thing, right? Otherwise, you don't see the ion beam. In our case, since the whole thing is negatively biased, ions are everywhere. So you can implant or process something like this, industrial component, you see a different shape material at the same time. Extremely useful and very fast. You understand the concept? The concept is this whole linearly biased. All the ions are attracted simultaneously, so we can process the whole area at the same time. Large sample, no problem, same time. So, in the beginning, I'll talk about microelectronics, semiconductor applications of our technology. Basically, sorry, I hit the wrong button. Because if you look at the way the process is carried out, the larger the wafer, you don't need the longer time because you're implanting simultaneously. So that means that even your larger size sample, it takes the same time. So that means the sample throughput is better for larger sample. In fact, commercially, right now, people are using the technology to implant silicon wafers using the microelectronic industry. You're talking about 2 wafers per minute. Very, very fast, 120 wafers per hour. So it's a very efficient process. And the good thing is the time is independent of the size, which is very nice. It's a good instrument and easy to control. Now in our laboratory, we have a number of programs. It's very broad. These are some examples of what we're doing. We work on a material called silicon insulator. I'll explain to you later on, using wave transfer and hydrogen plasma immersion harmonization. Also, we've developed a new process called plasma hydrogenation. We do shell junction formation for integrated circuits. We do high dielectric constant materials for devices. We do metallization in straight silicon, something that is a faster substrate for computers. We work on light and electron emitting materials, future devices, and also photovoltaic material, solar cell material. So this is a very broad area. We work on many different types of projects. And I also work with some collaborators here, like Professor Yan and so forth. Let me just start with high K, all right, which is very important. Now, this is the schematic of the basic structure of a microelectronic device. This is called an MOS transistor, metal oxide silicon transistor. Anybody know what this is? Have you studied this in courses? Any of you in electrical engineering? Right, so you know about this thing. But for those who don't know, this is basically a switch. This is the cross-section of silicon wafer. Basically, how we build devices, how we build computers and memories. This is a P-type silicon, and we dope these two regions called the source and drain N-type. So since it's a semiconductor, you can make it N-type or P-type. This is electron-rich, this is hole-rich. All right? And then here, if you connect this circuit, from the source, gate, and then on the channel and the drain, it's always open circuit because this is NPN. If one side is forward bias, the other side is always reverse bias. Right? It's NP and NPN. So you can never have a continuous circuit here. So that's the main point. How do you make current flow between these two? Make the middle N-type. Right? And the way to do that is to add an oxide, right here, called a gate oxide, put an electrode, apply, in this case, try to inject a positive charge, positive voltage here. What's going to happen if this voltage is large? The electron will be